Okay, right. So today we will be doing June 22 paper 42, and this is going to be alternative to practical paper. Right, so it's pretty easy. Okay, so to start with, a student determines the thickness of the glass in a test tube. The student uses a ruler and two rectangular wooden blocks to help him measure the external diameter of the test tube. Describe with the aid of a diagram how the student determines an accurate value for D. Okay, right. So for this part, what I can do is that I can, show this view that I have my, like the bottom of test tube here, then it's between two rectangular blocks, right? And these rectangular blocks are firmly pressing against my test tube, right? And I can place my ruler like this, right? So though not the best drawing, but I hope it gives you an idea, right? So basically, place the test tube, in between the blocks, measure the diameter using ruler. Okay, what you can do is that you can basically take a value at the end of one rectangular block and take one value at the start of like one rectangular block, and then you subtract both of them, right? So take the values from edges, around the test tube. Edges, I'm gonna make it particular edges of rectangular blocks around the test tube, and subtract to have a diameter volume. Okay, right, so that's it. What do they have for us? Student clamps the test tube in a stand. Okay, so this is a retort stand and the student has clamped the test tube. Fill the measuring cylinder to the 100 cubic centimeter mark with water. Pour some water from the measuring cylinder into the test tube. So basically we have a measuring cylinder and that measuring cylinder had 100 cubic centimeters of water, right? And what we did was we poured some of that water into a test tube, right? So what are we doing then? Now in here we can see the D diameter and H height. Yes, measure the height H of the water in the full size. So simply going to use a ruler, you're going to measure this. I think it's going to be like something like 3 centimeter, maybe larger than that, but approximately it's going to be like 3 centimeter, between 3 and 5, 3 and 4 centimeter, right? Then what are they saying? Figure 1.2 shows the volume VR of water remaining in the measuring cylinder. Okay, so this is the measuring cylinder, right? So what is the volume in measuring cylinder record VR? It's gonna be 89, right? Why? Because you count like this, like in this manner. So this is 85, 86, 87, 88, 89, right? So this is 89 cubic centimeter, right? So this is 89, right? And V is what? V is calculate the volume V of water in the test tube. So if this much volume of water has finished from the measuring cylinder, 100 minus 89 is the volume which will be going in the test tube, and that is 11, right? So this is gonna be 11. Right, so this is my answer for this, and H was like, let's give it a value of 3.0. I need to put a decimal because each and every value here has a decimal, right? Significant figures for all the values are not same, but all of the values have a decimal. So I need to ensure that I am not just writing 3, I'm writing 3.0. Or for example, if my value is 3.4, then I'll write the whole value 3.4, right? I tried to plot this graph, though this looks really bad. It should be a straight line, and you need to construct basically they have written here, construct line of best fit. It's not important that your line should pass through the origin, but what you need to make sure is that the line is as close as possible to your points, right? So you need to ensure that. So calculate the gradient.
कैसे बनानी है?
Basically, you have your points, right? Now you need to construct your line in such a manner so that it passes through most of the points. See, basically, if I'm going to try to
Like
construct a
line.
proper line, I cannot make
Mm-hmm.
a proper line. Okay? For example, from here to here, then from here to here, it's not going to be a straight line, right? I can only make a straight line when it will be passing through most of the points, but not all of the points, right? For example, see, it's not passing through this point. It is passing exactly through this point, right? It is passing exactly through this point, but it's not passing through some of the points, but it should be close to those points. Wait, let me show you also. Let me show you line of best fit. Give you an example. Wait. Line of best fit. Yes. Where is my screen? See, this is how line of best fit. See, it's not passing through all of the points, but it's close to all the points, right? And it's not passing through the origin. That's not important, right? It should be just close to all the points, right? See, close to all the points.
So line straight होनी चाहिए.
Yes, line should be straight. ठीक है. Acha, let's go back to the paper. It's the paper. Okay, so for this gradient, you're simply gonna use a formula, and that formula is what? M equal to change in y upon change in x upon change in x. So I am not sure about the point because see, for the gradient, you're gonna take 2 points on the line, right? So that's important. It can't be these points. It should be only the points which are on the line, right? But here I'm not sure which points are on the line, so I'll just take any 2 points from here, right? So that you have an idea of how to calculate the gradient. For example, now here I have V and H, right? So what I'm going to do is that V any, so 3, 5.6 and 79. Wait, no, it's V. So 5.6 and 21 and 8.9 and 34. 5.6 and 21, 8.9 and 34. So for example, these are my 2 points, and the units are not changing, so I don't have to convert it to SI unit. It's still centimeter here, right? And I also need to mention the unit of gradient, right? So what I'm going to do is, see, this one is x1 x2 y2, sorry, x1 y1. This one is x2 y2, right? So, and the gradient formula is m equal to, basically change in y means y2 minus y1, y2 minus y1 upon x2 minus x1. x1, where is x? Right now, see, I have, for example, I am considering these values x2 y2, right? So y2 is gonna be 34 and y1 minus y1 is gonna be 21, right? Upon x2 is gonna be 8.9, the same value, okay? 8.9, same coordinates, 8.9. So 8.9 minus 5.6. Let me see what this is gonna give me. Wait. This is gonna give 34 minus 21. 13 divided by 8.9 minus 5.6. So that is giving me 3.9, right? So my gradient is coming as 3.9. I actually calculated this because all the other parts will be related. Okay, otherwise my points aren't exact. My points should be on the line, and here I don't have a proper line. So that is why I just took this. So if the test tube is a perfect cylinder, then the internal diameter d is given by the equation. Okay, so pretty simple. M is the gradient, right? So you're simply going to put in your value that 4 into my gradient, which was coming as 3.9, and the unit of gradient is gonna be c. Unit also matters. C, change in y. So y has the unit cubic centimeter because v is on y axis, right? And h has the unit centimeter. Change in x, h has the unit centimeter. So cubic centimeter upon centimeter gives you square centimeter, right? So I'll just write the unit in case, right? So 4 into 3.9, which was my gradient, and upon, what is it saying? Pi. Here I cannot put the actual thing, so I'm gonna just put this, right? And to the power half. Right, so let's do that. I'm gonna 4 into 3.9 divided by 22 divided by 7, which is basically equal to 3.142. That, and then under root is giving me 2.2. Right, so I'm getting the answer 2.2 centimeters, right? Then we have your value for D is approximate. State one difficulty in measuring the height h of the water in test tube and suggest how this difficulty can be overcome. So height is this one, right? So definitely one very vivid fault here is that the surface of water is curved, right? So we cannot measure the height properly because the test tube is going to have the surface of water is not going to be stable, right? So that is the first thing, that it will be difficult to judge the position of the level of water, right? And another thing is that one very important point you can see here is that the bottom of the test tube is curved, right? So you can also write about that. Another thing you can talk about is that definitely we're going to measure this height using ruler, right? So it's also difficult to keep the ruler perpendicular, right? So, and then what are they asking? So for example, I am going for a pretty simple difficulty here. Difficult to keep the ruler perpendicular. And I'll tell you why I'm writing this one. Okay. I'm writing this one because whenever there is problem in keeping the ruler straight, in keeping the ruler perpendicular, you do what? You use set squares. How do set squares work? Set squares are basically those, like these things. Okay, I can't draw it. Wait, let me show you. Set squares. Okay, wait, let me show you also. See, set squares are basically these things. See, they're used to keep rulers perpendicular. Okay. So we can easily use that. And what else can we do? We can also clamp the ruler to keep the ruler straight. We also can clamp it. Clamp is the same as using this stand right here. Right, so you can clamp the ruler here, right? And then you can also measure the height of the test tube using that ruler, right? So you can also do that. And what else can you do? Place the ruler closer to test tube, perhaps. These are the things that are usually written in mark scheme, right? Whenever there is problem in measuring the height and you are measuring the height using rulers, there three things are must written in mark scheme. First thing is that use set squares. Third thing is that basically clamp the ruler. And third thing is that keep the ruler close to the object for which you're measuring something, right? So that thing. And then what are they saying? Suggest another reason why your calculated value for D is only approximate. So let's keep it simple. I think then test tube is not a perfect cylinder. Straightforward answer. So test tube is not a perfect cylinder, a uniform cylinder. So I think that's fine. Okay. Then we have measure the external diameter D of the, okay, so you're gonna measure this again, go back. And you will have to convert your centimeter. No, you will not have to convert it. It's already in centimeter. Acha, use your answers for E part 2 and G part I to calculate the thickness of the glass in the test tube. Okay, so so we have the internal diameter and we have the external diameter. Oh, right. Another thing here is that basically they were asking you why your calculated value for D is only approximate. So see, this one is the calculated value, right? So if I'm talking about internal diameter, then there can also be problem because of the water, right? See, diameter of the water can be measured by that of, right? Basically, when I'm measuring the internal diameter, what will affect the readings? Water inside the measuring cylinder will also affect the readings, right? But water sticks, right? This is the property of water, that adhesion and cohesion is the property of water. In simple words, water molecules stick to the surface of any object it is within, right? So because of that, because water sticks to the side of the measuring cylinder, that makes the reading inaccurate, right? So that can also be one more reason, because they're talking about the internal diameter, right? Okay, so you have the internal diameter and you have the external diameter in your answers, E part 2 and G part I. And the formula for calculating the thickness of the glass using your internal and external diameter is that you basically subtract your internal diameter from your external diameter and then you just divide by 2, right? And it is basically in centimeters, so you don't need to convert as well. But wait, I need to have a value for external diameter. Okay, so if I look at the external diameter, this is the external diameter. This is like approximately 2 centimeters, but it's like a little bit more than 2 centimeters. So let's consider it like 2.3 centimeters, right? So I'm taking an estimate. So for example, if my answer is 2.3 centimeter right here, right? So how am I going to calculate? I'm going to subtract my internal diameter from external diameter, right? So this was my external one. My internal was 2.2, right? And divided by 2. This is the formula for calculating the thickness, right? So that is going to be 0. Okay, let me do it. 2.3, 2.2 divided by 2. So this is giving me 0.05, right? Then what do we have? Student investigates the cooling of hot water in a beaker. The student measures the room temperature before starting the investigation. The room temperature is 24 degrees Celsius. Okay. Student pours 150 cubic centimeter of hot water into a beaker, places a thermometer into the hot water, and then waits for 30 seconds. Okay, so why is the student waiting for 30 seconds? That's the first question in our mind. Okay. Records the initial temperature of the hot water and starts a stopwatch. Records the temperature theta of the hot water every 60 seconds for 300 seconds. Okay. Suggest why the student waits for 30 seconds before reading the initial temperature of the hot water. Okay. So why would the student wait? So that the reading becomes stable, so that it stops increasing, right? So that's it. So that reading becomes stable. temperature stops increasing. Okay. Then we have calculate the average rate of cooling R1 of the hot water during the first 60 seconds. Use the equation. So pretty simple. You already have the temperature. So what you need to do is simply put in the formula, right? So theta 0 is 89.5 and this is 83 divided by 60, right? So you need to write this, right? You're not going to get the mark until unless you put in the values and then you show them that you're doing this, right? So my answer is going to be 89.5 minus 83. Sorry, 89.5 minus 83 minus 83 and then divided by what? Divided by 60. So that is giving me 0.108. 108. Have they mentioned significant figures? No, they haven't. So I'm going to just write it according to how I seem appropriate. Right. Then we have R2 between 240 and 300 seconds. So that is going to be 240, 66. So 69 minus 66. Okay, divided by 60. So that is going to be give me 0.05. Right. Just put your values in the formula, write it down, and then calculate it, right? That's all I'm doing here, right? Then what do we have? Use the values you calculated in part B to describe how the rate of cooling of the hot water changes as the hot water cools. Here the rate was 0.108. Here the rate is 0.05. What happened to the rate? It decreased, right? So simply rate is decreasing as the calculated values for rate above calculated values for rate above decreased from 0.108 to 0.05. Okay. At the end of the investigation, student leaves the water in the beaker, predict the final temperature. So very easy. If you leave something, so basically, if you're gonna leave something, if you leave something for a very long time, what happens? It eventually reaches room temperature, right? And room temperature is already written here. So what is its final temperature gonna be? 24, right? Suggest how the student ensures that the temperature readings are as accurate as possible. Okay, so whenever you need to ensure that your readings are accurate, what you need to do is, first of all, you're measuring. First of all, whenever you're measuring temperature, whenever you're taking temperature readings, first thing that you need to do is definitely you're gonna look at the thermometer, right? So chances of parallax error, right? So first thing that you need to do is that your line of sight should be perpendicular to the scale of the thermometer. Line of sight should be perpendicular to thermometer. Okay, this is the first thing. I'm gonna write 3 things that you need to do whenever you need to take accurate temperature readings. Okay, you can use digital thermometer, immerse 1/3 of thermometer whenever you're taking readings. Okay, and stir. Fourth thing also stir. Like these are the 4 things that you do whenever you need to keep the temperature readings as accurate as possible. 3 students A, B, and C measure the speed of sound in air. Students A and B stand at opposite ends of a football pitch. Student A strikes 2 large blocks of wood together. Student B starts to watch when she sees the blocks hit each other and stops to watch when she hears the sound. Students repeat this procedure twice. Student C measures the distance D between students A and B. The times they recorded are shown. Okay, so how are you going to calculate the values? Simply add them up and divide by 3 because the 3 values, right? So 0.45 plus 0.41, 0.45 plus 0.41 plus 0.51, and then you're going to divide by 3. right? So that is gonna give me 0.45 is 0.51 plus 0.41 and then divide by 3. So that is giving me 0.456666. So you can round it off to 0.46, right? So that's it. The distance between students A and B is 190 meters. Suggest a device. Definitely, it's a very long distance, right? So what can you do? You can use measuring tape. Measuring tape. Calculate a value for V, the speed of sound in air. Use the equation. Okay, so D is 119. Time is this. So 119 divided by 0.46 is gonna give me. It's giving me 258.69565. So I can round it off to 257. Sorry, 259. So 250, I'm gonna write to the nearest decimal actually. So this can be my answer, right? Then what are they saying? Just one, okay, what I did was, right, I divided 119 with this, right? And you need to write it down here, right? So you need to write it down. You're not gonna get mark until unless you mention it, right? So I'm gonna mention this. Suggest one reason why the value calculated in V bar 2 for the speed of sound in air is only approximate. Okay, so why would a speed value be approximate? Because when you're calculating speed, you're using this formula, and in this formula, time, you have an error for time, and that error is called reaction time errors, right? So basically, because time can be inaccurate, recorded can be inaccurate because of reaction time error. Reaction time error. Okay, that's it. Then what do we have? A student investigates how the resistance of a filament lamp changes when the current through it is varied. So this topic we just did, recently did, right? So this is really going to help you, revise those topics. Student connects the circuit shown in figure 4.1. Right? So student connects the circuit shown in figure 4.1. Student has connected the circuit inaccurately. Okay, incorrectly. Why? Because you need to calculate the resistance of filament lamp. And we just studied, if we want to calculate the resistance of filament lamp, the voltmeter should be across the filament lamp, not across the rheostat. Right? So it should be, how should it be placed? It should be right here. This thing is my voltmeter. Right? This is how it should be. An ammeter should be in series with the filament lamp because I need to measure its resistance, right? So this is gonna be my ammeter, right? So I redo the circuit. I'm gonna remove this, right? Remove this. When you have to redraw the whole thing, so you're gonna remove this, and draw this. Okay. When the switch is closed in the corrected circuit, the student observes that the lamp does not appear to light up. Filament of the lamp is not broken and the battery is not run down. What observation the student make to confirm quickly that the filament of the lamp is not broken? Okay, so what will tell you that the filament of the lamp is not broken? When your ammeter is going to record a reading, right? Because if the filament of the lamp will have been broken, current will not be able to pass through, right? So if we have a value for current recorded in the ammeter, that shows that the filament of the lamp is okay, it's fine, right? So ammeter will record a value, records a current value, right? That's fine. Then we have suggest why the lamp does not appear to light. Okay, so when will the lamp not light? Okay, what do we have in the circuit? We have a rheostat, right? And what does the bulb require to light up? Requires current, right? And when is current low? Current is low when resistance is high, right? So current of your rheostat is high, because of which current is very low to light up the lamp, right? Resistance of rheostat is very high. So current is too low to right. So I think that's it for this paper. Okay.